All right, good afternoon, everybody. Let's get started. So, welcome to 644, and congratulations to everybody for being done with quiz 1. We are very happy to see that the average was quite high, so most of you did quite well. In fact, this was the highest average in several years. And the standard deviation was also lower than in previous iterations. So that said, if you did poorly on quiz 1, or you are concerned about your grade, now is a good time to reach out and let us know. There are resources. We can sit through with you and figure out what is it that you need some help with. But please reach out so that we can help you. All right. So with that, today we're going to actually have the last lecture on sequential logic. And in fact, in this lecture, we're going to do two different things. In the first part of the lecture, we're going to finish the discussion of pipelining, which we started last lecture, and then look at essentially putting all these design trade-offs that we've seen over the past couple of lectures together and seeing how we can compose different styles of circuits, especially how we can compose pipelines and mix them up with other styles of circuits. And then in the second part, or towards the end of the lecture, we'll start looking at a different kind of trade-off, which is that so far we've looked at how to build special purpose hardware, right? So now if I give you some C code or some Python code, you can go and build a module, right, a mini-spec module for it, and in some cycles you can compute the answer. We'll actually start seeing how we can generalize a single FSM so that we can implement multiple algorithms with the same hardware. And that is the first step towards building a general purpose processor, which the lecture on Thursday will be all about. So, now that we have seen different kinds of circuits, combinational logic, sequential logic, multi-cycle, and pipeline circuits, we have sort of enough background to grasp what is the key difference, the key conceptual difference between designing software, right, writing programs, and designing hardware, right, writing circuits. And it's all about the timing, right? So something that is kind of implicit, but actually once you see it, it's very obvious, is that every interface we've built so far in software and in your programming language courses, what you'll see is that all software interfaces, objects, method calls, processes, and so on, they're all timing independent. What I mean by that is that you're specifying, when you write a program, you're specifying what should happen, but not when. Right? So for example, if you have this loop, right, you can implement this loop all the way down to assembly with 4 instructions here. And this instruction will call some procedure, which will take some amount of time. But even if you didn't call this procedure, of which we don't know the implementation, we actually don't know how many nanoseconds these instructions are going to take. And so we can't really say how fast is this code, right? We have some expectation. Maybe our processor says, well, I'll try to execute 1 or 2 instructions per cycle. And, we'll get some rough idea of how fast this code is going to be. But you actually don't know how long it's going to take. And this is good because it's simpler. Right? I don't want to be concerned with, telling the machine in 1 nanosecond I want the output of this, right, or this instruction to be done. In the next nanosecond I want that other instruction to be done. Now, hardware, on the other hand, is all about timing, right? So everything that we've been doing, whether we draw pictures of FSMs or we implement mini-spec modules, is all about specifying the combinational logic sandwiched in between registers, right? And then the delay of that combinational logic is going to itself determine the clock cycle, right? So we're going to specify what happens in each cycle, which in and of itself is going to tell us how fast the circuit can go. So we have a very precise idea of when is our output going to be available, or how fast is the circuit going to go, right? And everything else, right? If you look at a hardware description language versus a software programming language, everything else is syntax differences, right? But this is the one fundamental difference. In fact, there have been some attempts to translate this kind of software description, timing independent description, into hardware, and except for particular patterns, this is still an open problem. There are some tools, but they don't work well in general. Okay, so over the past 2 lectures, we've seen different benefits of sequential logic, right? So first in lecture 11, we saw that sequential circuits can implement more computations than combinational circuits can. That is, there are some problems for which we can write or design an effective sequential circuit, things like find me the factorial of a number, or the GCD of 2 different numbers. But we cannot write an efficient combinational circuit for it. And that's because either these circuits take a variable amount of input or output, or because they take a variable number of steps, right? And so we can't express a variable number of steps with combinational logic. Then, in the last lecture, we saw that even when you can implement something with a combinational circuit, by having, by throwing sequential logic into the mix, by adding state, we actually have more design trade-offs. We have more styles of design. So on the one hand, we saw pipeline circuits, which are all about improving throughput by adding pipeline registers and essentially breaking a combinational circuit into multiple pipeline stages. And that allows us to increase to increase the clock frequency, that is to decrease the clock period, run more outputs per second, or more inputs per second throughout that circuit, and therefore get higher throughput. On the other hand, we have folded circuits. We also saw a little bit of folded circuits, which are the opposite, right? So they're exploiting that a lot of combinational circuits have repetitive logic to essentially reduce area by using the same block of logic and then reusing it over multiple cycles. And that essentially reduces throughput, but also reduces area. I have a little bit of feedback here, so. Okay, that should be better. Okay, so as a reminder, the key idea of pipelining. So pipelining is a scary word, but it's actually a very, very simple concept, right? So suppose you have this circuit over here, right? And so this has a propagation delay that's set up by, that's determined by the slowest input to output path, right? And so what pipelining does is it breaks a combinational chunk of logic over multiple stages, right? Multiple pipeline stages separated with registers. So here, if we have these registers separating, the outputs of F and G and with the inputs of H, and then separating the output of H, what we've done is we've created a 2-stage pipeline. We call this the first stage and this the second stage. And this now has a major benefit over the combinational circuit, right? The propagation delay of this circuit used to be 20 plus 25, 45 time units, let's say 45 nanoseconds. What is the propagation delay of this pipeline circuit? What circuit here is the one setting the propagation delay of every input to output path? Or every register to register path? Sorry? So we have, what is the propagation delay between X and this circuit? Well, the propagation delay of each component is given in the component itself. So you have 15 time units here, 15 nanoseconds, 20 nanoseconds, and 25 nanoseconds between these registers, right? What does that mean? This means that we can now clock this circuit faster, right? So assume that we have ideal registers. Now we can set the clock cycle time to 25 nanoseconds, right? So we can give, so before we had to give one new input every 45 nanoseconds, right? And then wait for the output to become stable. Now we can give one new input every 25 nanoseconds, right? So our throughput goes up. We can do more computations per second. But the trade-off is that now we're going to take 2 cycles to get the value that we want, right? So this is essentially, very obvious from looking at the pipeline diagram, which we said this is sort of the standard way to represent pipeline circuits and how data flows through a pipeline. And so in a pipeline diagram, you have 2 dimensions. On the x-axis, you have cycles, you have time split in cycles. On the y-axis, you have pipeline stages, right? And so here we have 2 pipeline stages. The first one, which is the one that has F and G, and then we have the second stage, which is the one that has H, right? So as you can see, at cycle I, we give some input x of I, and then the first stage works on it for this cycle. Then on the next cycle, the second stage gets these inputs, right? Gets f of x of I and g of x of I, right, at cycle I plus 1. Then, at the end of this cycle, it writes the output to this output register. As a result, over this cycle, in cycle I plus 2, this register holds the output that we want, right? So now our latency is the clock cycle time times the number of pipeline stages, right? So in this case, we're going to take 50 nanoseconds to get the output, right? So pipelining always is a throughput optimization. It's never going to reduce latency, right? Latency counted end to end, right? Of course, a single stage is going to be faster, but because you're going through multiple stages, the overall time that you're going to take to get a single result from input to output is going to be larger, right? Equal or larger. Okay, any questions? This is important, so if you're confused, including if you missed the previous lecture because it was a quiz, please say something, because we're going to talk about pipelines quite a bit, and if you don't understand these concepts, this is going to be very confusing. Okay, so last lecture we saw different ways of pipelining a multiplier circuit. So multiplier, we started with the combinational implementation, which is shown here. This looks kind of scary, but it's actually quite simple. Each row is implementing addition of 2 4-bit numbers. So this multiplier specifically is a 4-bit multiplier. It's multiplying 2 4-bit inputs A and B. And so then what we do is we first compute the partial products of basically multiplying B, the input B, by each particular bit of A. And because in binary multiplication is just an AND gate, these partial products are very easy. We've all learned fairly large multiplication tables, right, in middle school. Well, my favorite thing about binary is the multiplication table. It's as simple as it gets, right? So you don't need to do anything complicated to compute these partial products. This is just an AND gate. It's either 0 or the original input. And then each of these rows is adding up 2 of these partial products, right? And as we move down, we have n partial products. To add them all up, we have n minus 1 adders. So in this case, because we have 4-bit inputs, we have 3 4-bit adders, which in this case, we've gone ahead and run them as ripple carry adders. And there's one detail here that you have both full adder blocks and half adder blocks, and remember that this, full adder is just as we saw, it adds up 3 1-bit inputs and produces a 2-bit output. A half adder adds 2 1-bit inputs and produces a 2-bit output. Right, so a half adder is going to give you an output that is either 0 0, 0 1, or 1 0, but it's never going to produce 1 1. Okay, So if you look at this combinational implementation and then generalize, right? So for 4 bits, we have 4 times 3, so 12 blocks, right? But if you look at the area in general, as the number of input bits grow, right, you're going to have n blocks times n minus 1, right? And so the area of this circuit is order n squared. Now there's one funny thing with this circuit which we saw last lecture, which is that the propagation delay is actually not quadratic. Even though each of these adders has a linear propagation delay, and you have a linear number of adders, because these adders are skewed, you don't actually have n squared delay. And so there are multiple worst case paths through here, but one of them, just to see this more clearly, is this one, right? So basically anything that ends up, comes from one of the top inputs and then ends up at the bottom left output is going to have the maximum number of other blocks or 1-bit other blocks between it. And so here, if we just count, you have 4 blocks plus 2 plus 2, right? But so if we generalize, you're going to have n blocks and then n minus 2 times 2, right? So you're going to do this step. If you imagine that I had n bits here, we do n minus 2 of those, and then times 2 blocks that we cross, right? So in that case, the general formula for how many delays you have is n plus 2 times n minus 2, so 3n minus 4. And 3n minus 4 for 4 bits happens to be 8, which, yes, matches what we have here. But forgetting about the constant factors, this is order n, right? This is an order n delay. So now, for a combinational circuit, what is the latency? So remember, we're always interested in 2 different performance measures: latency and throughput. How many results, how long does it take, right, to get 2 inputs, from the time that I put 2 inputs in this circuit until I get a valid and stable output? The propagation delay, right? So the propagation delay itself determines the latency of a combinational circuit. So the latency is it's exactly the propagation delay. How about the throughput? Well, if I clock this at maximum frequency, then how many results could I get per second? 1 over. Yes, I see some of you doing. So 1 over the latency, so 1 over n. Right? So the problem here is as the number of inputs grows, we get less throughput. Right? So then we said, we could pipeline this. And there are multiple ways of pipelining this multiplier. One thing you could do is put pipeline registers between every row. Problem is that the delay of each of these others is still linear. And so there's a much better way of pipelining multipliers, which is diagonally. So if you draw the pipeline contours, like so, you see that between every pipeline stage, you have only a single other block. Right? Because we're cutting all the carries. You see? We're putting a pipeline register between all the carry chains by pipelining diagonally. So, if you pipeline this way, let's now look at the design trade-offs here. Now our area is still order n squared, right? Because we have also order n squared registers, 1-bit registers here, but we have order n squared combinational logic, so no change in the asymptotics there. How about the propagation delay? Put differently, how fast can I clock this circuit? Does how fast I can clock this circuit depend on the number of bits of the input. I see some of you saying no, right? So that's because I always have a constant amount of logic between each stage, right? So my clock cycle time is now constant and very small. Now the trade-off is that I have order n stages. In fact, I have 3n minus 4 stages in general. Here I have 8 pipeline stages, right? So now what's the latency of this circuit? Right, so from input to output, it's going to take n stages times the clock cycle time of each stage, right? But the clock cycle time is constant, so latency still grows linearly, right? I haven't actually improved latency. However, this dramatically improves throughput because now we get a constant throughput regardless of how many input bits you have. Right, so throughput is a factor of n better by pipelining than in the combinational case. Right, we have an n-stage pipeline. We've increased throughput by a factor of n. This is not a trivial increase. Right, if you have 32-bit inputs, we're talking about the difference between a circuit that could run at, let's say, 50 megahertz and 4 gigahertz. Right, so it is quite an important optimization. Okay, any questions? All right, so the other style of circuit that we saw was folded circuits, right? And so combinational circuits often have repetitive logic, as we've seen with the multiplier, right? So an n-bit multiplier has n minus 1 adders. And so the idea here is that instead of having all those adders, we can use less combinational logic, for example, a single adder, and then reuse it over multiple cycles. Right? So this is a possible implementation for a folded multiplier, where on each cycle we're computing a single addition, right? And then we're adding up these partial products. There are some shifts that need to happen, between A and P. And if you look at this particular code, there's A is actually reused to hold some of the bits of the output, which is sort of an implementation detail that you'll deal with in the lab. So I don't want to spend a lot of time sort of explaining this implementation in full detail because you will see it in lab 5. But the key trade-off here is that instead of having all this logic, right, we're effectively implementing only this amount of logic, right, only one row, and then we're just reusing it over multiple cycles, right? So we get less area, but also less throughput, right? Okay, so let's just go back and take a look at all the different design alternatives that we have seen. So let's say we have some function, right, that requires 3 combinational blocks, F1, F2, and F3. So a combinational design that in this case is sandwiched between pipeline registers. So this would be a one-stage pipeline, and then it has some input pipeline register from some other block. You can see that each input has to go through all the blocks, and so that is going to set the clock cycle time here, right? So we are not overlapping inputs. On each cycle, this circuit processes a single input end to end. In a pipeline, on the other hand, as you can see here, what happens as clock cycles go by is that we start overlapping multiple elements, right? So this stage is computing, it's processing the blue element over here, while this stage is processing the green element over here, while this stage is processing the red element, right? And so we're getting one output per cycle, right? And the key benefit is that we now can increase the clock frequency, reduce the clock cycle time, and increase the frequency, and so get more outputs per cycle. Finally, in a folded implementation, what we do is we reuse the same block, right? So if these Fs are similar, then we can just have a single F and then have some additional peripheral logic so that the same output is processed or the same input is processed over multiple cycles, and we compute the output after some time, right? And only then we take the next input. Okay, so let's take a look at the 3 trade-offs here. right? So the clock cycle time, from these implementations, which design is going to have the longest clock, right? Which is going to be the slowest clock? The one that has all the combinational blocks in, right? So A is going to be the one with the highest propagation delay and therefore the highest clock cycle time. And then between B and C, there's one F between each register, and there's some additional logic here. So typically C is going to be clocked a little bit slower than B, but that's basically an implementation detail. That's in the noise. They're typically about as fast. How about the area? Which of these implementations is going to have the smallest area? Is going to be the most area efficient? C, exactly. And then, between B and A, well, B is always going to be the most expensive, right? Because we're adding all these pipeline registers, and so that's always going to add some area. But, A and B often, if your combinational logic blocks are large, are about the same area. How about throughput? Which of these implementations is going to have the highest throughput of all of them? Is it going to be C? No. Okay, it's going to be B, right? Because it's the implementation that we can clock at the lowest clock period, right? So we can clock it the fastest, and so we can get more results per second out of this pipeline implementation, right? If the F blocks are about the same propagation delay, then this will be about 3 times as fast as A, and then C typically is a little bit slower than the combinational version. So it depends. It can be pretty close because the clock cycle time can often be made much, much shorter. But if this has some parallelism so that you can start doing things as trees rather than as chains, then the combinational version in general is going to be a little bit faster. Okay, any questions? Okay, so in the rest of this part of the lecture, I want to just quickly go through a few issues with pipelining that have to do with combining our circuits into a larger system. So the first thing is, so far, when we've been looking at throughput and latency, we've assumed that we can choose whatever frequency we want given the circuit that we've been looking at, right? So for example, if you go from a one-stage pipeline to a two-stage pipeline, as we saw in the example, in the first example I showed, right, where we went from a propagation delay of 45 nanoseconds to 25 nanoseconds, we said, well, that means that we can lower, we can go from a clock cycle time of 45 to a clock cycle time of 25, and that means that we're going to get higher throughput, right? If you were doing a folded implementation, or you were, reducing clock cycle time in some other way, for example, with a combinational circuit, if you were reducing the latency of a combinational circuit or the propagation delay of a combinational circuit, you could also lower latency. Now, in a real system, typically what happens is not that you can set the clock as high as you want. First, because you're designing one thing at a time, and so you're going to have other circuits that are going to set the propagation delay if you start, if you keep pipelining or if you keep reducing your own propagation delay. And also, and this is especially important these days, because most systems today are power limited. So you cannot clock them as fast as you can, given propagation delay, without burning the chip. So just because of power consumption, sometimes we will have some artificial constraint in the chip. They will say, well, for this power consumption, you cannot run above 3 gigahertz, even if your circuits can tolerate 5 gigahertz. So given this changes the sort of analysis that we've been doing, right? So if reducing the propagation delay does not let us reduce the clock cycle time, these trade-offs actually become quite different. And so let's see this with a specific example. Let's say that I give you a two-stage pipeline, right, and you go and add divide each of the stages into 2 stages, do it in a very balanced way. So you get a 4-stage pipeline that's same propagation delay across all stages, right? And so if you take the propagation delay of the original 2-stage pipeline and cut it in half, ideally, right, you can, if you have no other limitation on the clock, now you can go and clock this twice as fast, right? Set the clock cycle time to half of the clock cycle time of the 2-stage pipeline. In that case, what happens with throughput? If I clock something twice as fast, what happens with throughput? How many more results per second can I get out of my circuit if I clock it at twice the rate? 2x. And the latency is going to be 1x, because even though we're doing 4 stages, each stage is half the time. Now, if on the other hand, there's some other limitation, right? There's some other circuit that's limiting the clock cycle time, and we cannot, despite going from 2 to 4 stages, we cannot increase the clock cycle, we cannot decrease the clock cycle time, then these trade-offs completely change. So we're not going to get any extra throughput, and in fact, now this circuit has more latency, right? Because we're going through more stages, and each stage is just the same, right? The same latency as before. Okay, so when you're designing circuits, and you'll get a couple of questions on this in lab 5, you'll have to deal with some of these limitations. Now, there are other things. The last part of pipelines has to do with essentially some circuitry that we generally need to add, because pipelines are not alone in the system. So far we've seen, you have this pipeline, and you get one input every cycle, and you produce one output every cycle, and that's it. Right? But in general, we're going to have some circuit that's producing inputs, and some, so we'll call that the producer circuit, and then some consumer circuit that's taking the outputs that we produce. And these circuits are not necessarily pipelines, right? So they're not necessarily producing something every cycle and taking in something every cycle. So in general, the producer may not have an input every cycle, and so there are some things that we need to do to address this. The simplest thing is we'll see how to add valid bits to the pipeline, so that we can keep track of which stages are processing valid versus invalid data. On the other hand, the consumer may not be able to take an output every cycle, right? Maybe this is some circuit that takes multiple cycles to compute, to process each output, right? Or maybe on average it takes 1.5 cycles, so many inputs take 1 cycle, but in some cases it goes and takes 10 or 100 cycles. And this we will see, when you build processors, you'll see that this is precisely how memory behaves. We're going to be able to build a circuit that on the common case takes 1 cycle, but sometimes it's going to take 100. And so in this case, what we need to do is pause the pipeline or freeze the pipeline. And to do that, we'll add stalling logic. Finally, there's this detail that will be very useful in the design project, although not quite at this point. In lab 5, you won't get to use this last bit, which is that if you have a very large pipeline, you actually need some more flexible control. And so we'll see how to do that, to get that flexibility by using queues instead of registers. Okay, so the first order of business is, if the producer doesn't give us an input every cycle, then there's a very easy solution to this. We just stack each stage with a valid bit. And so, as you saw in the recitation for lecture 11, in minispec, this just boils down to using maybe types. So you have a valid output from this producer, and basically we just propagate it, right? Add 1 bit to its pipeline register that tracks this valid state, right? So now the way this shows up in the pipeline diagram is that we can have, each cycle, the producer can give us either a valid value, shown here in different colors, V1, V2, V3, V4, V5, or an invalid value. And so these invalid values are shown in red. And so what you can see is that with these valid bits, what we do is we essentially track how these invalid values propagate throughout the pipeline, right? So every time you get an invalid value in, that in this case, since this is a three-stage pipeline, 3 cycles later, this will show up as an invalid output in the pipeline, right? Okay, so that's sort of the simplest extension we can have. Let's look at the other side of things. So if the consumer cannot take the output every cycle, then we need to freeze the pipeline, and in fact we need to freeze the producer too, because the producer can't keep giving us inputs if we can't give any output, right? And so this is done just with a single signal, with a single wire that we call stall, and then we're going to have registers with enables, right, or with something very similar to an enable circuit. So if stall is true, then this register does not take what's at its input, it just retains its current value, right? And so by just setting stall to 1, the consumer can freeze the whole pipeline and the producer for that cycle, right? So let's take a look at how this looks. So here you can see that we have the 3 stages, right? So we have stage 1, stage 2, stage 3. Right, and then we have this stall output. And note that because of how pipeline diagrams work, on each cycle, what this cell shows is the value that is being processed by each particular stage, right? So let's say that we have V1 traversing the pipeline, and at the end of cycle 3, now the output register in cycle 4 is going to have the value of V1. The consumer sees this is a valid value, and let's say it's implementing some multi-cycle computation. It says, I can't take any more values, right? So freeze the pipeline, right? So the next cycle, everything, right? Every pipeline stage is going to retain its all value, right? And the producer is also not going to be able to enqueue anything into the pipeline. Then, in this cycle, let's say the consumer sets stall to false, so now the pipeline keeps making progress, right? So every time, every cycle, the stall is true. On the following cycle, you can see that there's no progress being made in the whole pipeline, right? We freeze the pipeline and we don't let values propagate through it. Okay, any questions so far? Okay, so let's just make things a bit more interesting. Suppose that you have both valid bits and stall logic. Now you could treat these as independent optimizations, but you can actually do something smarter, which is that you can still let the pipeline make progress if the consumer wants to stall, but you have an invalid value in the middle. So let's first ask ourselves, if you had an invalid value in this output register, right, and the consumer told you to stall, why not say, well, I want to stall, or the consumer wants to stall, but the output is invalid, I don't care about it, let's just not. Right, so this is just an AND gate. So if stall is 1, but valid is 0, this output is now 0, and the rest of the pipeline doesn't stall. And so what happens is we just crash the invalid value in the next cycle, right? And we repeat this procedure for every pipeline stage, right? So now how does this look, right? The pipeline diagram gets much more interesting. So here you have valid values progressing through the pipeline like before, but then on cycle 3, the producer doesn't produce a valid input, right? So we have an invalid value. Then on cycle 4, this invalid input is being processed, or is in this state, right? So this pipeline register is invalid. Now, what happens is the consumer sets stall to true. So the next cycle, these 2 stages retain their inputs. But this one says, I actually don't have anything useful, so I can keep making progress, right? And so you can see that on the next cycle, V1 and V2 are exactly the same as before. We've frozen these two stages, but these two stages make progress, right? And we've just eliminated one of the invalid values, right? Okay, any questions? So, there's one last issue that we're going to see very briefly, because you won't need this until the design project. And let me just tell you about the intuition of this. We have this wire, right, that goes from the consumer all the way to the producer. And if you built your entire system like this, it would be madness. Now, in circuits, right, we can just think about this stall logic. Imagine that you have 50 pipeline stages, right? This is going to drive the enable signals for lots of registers, right? And just driving those signals is going to incur a lot of propagation delay. And so what happens is that, first of all, this stall signal is typically something that you derive in the middle of the cycle. So you already have some propagation delay, because the consumer is trying to figure out, can I do something the next cycle, or do I have to tell all the people upstream to stall, right? And so if you stall, you're already generating this signal sort of in the middle of the cycle, and now you have to drive all these outputs, right? All these register inputs. And so what that means is that if you keep adding pipeline stages, the stall delay increases, and eventually that's what sets the propagation delay, and that's what limits the clock cycle time. So you keep adding pipeline stages, and your clock cycle time goes up. It's not even that you cannot get it down, it's that it just gets worse. Okay, so if you think back to real life, if you're a reasonable driver, what do? If you're in the highway, you don't drive bumper to bumper with the car in front of you, right? You leave yourself some space, so that if the person in front of you brakes, you still have some space to brake with a little bit of delay, right? Now, if you're a Massachusetts driver, you just drive bumper to bumper, and so that's why the mass spike is how it is. But out-of-state drivers or reasonable people will leave some buffer, right? So this is the same thing, right? You can solve this problem by using queues. If you leave yourself some buffer between stages, now you can let other stages make progress while you're still, or while you need to stall. And so, we're not going to go into a lot of detail of this queue implementation, but let me just tell you at a high level how it works. So instead of a single pipeline register, let's say we have a queue with 2 elements, right? And so this holds up to 2 values. And then it always outputs the value that you enqueued first. And there's a dequeue input that controls whether to advance the queue, right? So if the queue is false, then you freeze those values. Otherwise, the value in the second register goes to the first, and so on. And then there's an isFull output that tells us whether both values have valid or hold valid, or both registers hold valid values. Now there's multiple ways to implement this queue. One possible implementation is as shown here, where we have these 2 registers with valid bits, and then the isFull output is simply an AND of both valid bits of both inputs. There's a little bit of complication on what value do you take in each register, but the high-level logic is very simple. Basically, E1 is going to fit into E0, E0 is going to be the output register, and then there's this max here because we don't want to waste a cycle if the queue is empty, but we have a value to enqueue, right? So if there's nothing here and nothing here, we'd like to just enqueue it directly to E0. And that's why you see these maxes, and sometimes E0 can take the enqueue input. Now, here's the code for it. We're not going to go through it. In the recitation, there's a problem that asks you how to implement an n stage or an n element FIFO with actually simpler code, or at least more systematic code than this one. Okay, so if you do this, now we can have the stall logic drawn up like this. Why? Because since we have 2 elements here, we only need to stall, or we set stall, which is not dequeue, right? So this is the isFull right? So we have DQ is full, DQ is full, right? So if we have our upstream stall set, then we don't DQ, and then if this is full, then we stall the next, right? Now, the trade-off here, of course, is that you cannot enqueue in this design to a full queue, even if an element is being dequeued on the same cycle. And so that has to do with the way that we've built the FIFO to not have a combinational path between is full and DQ, because if we had a combinational path between is full and DQ, then we would have to, we would be sort of back again into the problem of having a very long chain of logic. But beyond the details, which as I said, you'll probably need only later in the design project, the key takeaway here is that if you leave some space, if you leave some flexibility between stages, you actually don't need to incur this huge propagation delay. And also in general, queues, you can have queues with more elements, which are useful if you have irregular rates, right? So if the producer and the consumer are sometimes very fast, but sometimes very slow, queues allow you to essentially account for that delay or tolerate that variability in delay. Okay, so in the last couple of minutes, I want to start going, moving from how to design FSMs to how to design general purpose processors. And so in 6L04, up to this point, apart from seeing RISC-V, on the hardware side of things, we've seen essentially all this hierarchy of techniques and abstractions. And so now, we know how to take a problem and essentially build an FSM that solves the problem. What we're going to do next in 004 is go and build a general purpose processor that can solve any problem, right? So long as the processor has enough time and memory. And to see this, the first step that I want to go through today is to take an FSM and generalize it. And so to do this, let's just take the factorial, or one possible implementation of the factorial FSM. And just as motivation for this, if you think back to all the circuits that we've seen, right? So in lecture we saw the implementation of the GCD circuit, but then in recitation we had the factorial circuit, we had the Fibonacci circuit. See that they all have the same kind of structure, right? There's registers, there's operations, there's muxes to control what input the registers take. And so to see how to do this systematically, you can take factorial, which is shown here in Python and C. But remember, when we're designing sequential logic and when we're designing hardware, we want to specify what happens cycle by cycle. So one systematic way of doing this is with what we call a high-level finite state machine, where essentially you describe what's happening on every cycle. On each state, you have all the register assignments that are happening in that state, and then transitions between states that depend, are either always transitions between consecutive states, or you have Boolean conditions that determine whether you stay or whether you transition between states. So now you can go and take this FSM and design both, this bottom part over here, which we call the data path. And so this is very similar to what we saw before. Systematically, you basically implement the register. So here we have two registers, A and B. Then we have different assignments that are happening at different in different states, right? So in the start state, we want to assign 1 and n to A and B. In the loop state, we're going to assign A times B to A, B minus 1 to B, and so we have combinational logic for those, and then A and B for the done state, right? And then we just have a mux at each of the inputs controlled by a different select signal, right? So this is sort of systematizing what we've already been doing with designing FSMs. Now, you can look at the upper part and say, well, there are 3 states here. This is a very simple FSM, right? You can totally do this FSM, right? This is just 2 bits of state. And so if I give you, the circuit, the description of the circuit, you can write a truth table, you can implement it in minispec. This is, without going into the details, essentially you can set the mux inputs, right, using both a little bit of state and then some output from, in this particular case, from this comparison with 0, right, which is what determines where you stay in the loop state or go to the done state. Okay, Now, the problem is that you have a single data path, and you can do factorial with it. And you can actually, if you look at this circuit, with this same circuit and a different control FSM, right, you can do a few more things. You can do multiplication. Obviously, you have a multiplier there. But you can also do things like squaring. But you cannot do many things. And that is because you have only a few registers, only a few operations, and only a few inputs to the control FSM. So what is the key idea that underlies general purpose processors? Well, it's very simple. The first thing that we're going to do, and this we'll start on the next lecture, is we'll create a programmable data path. We'll generalize the data path. So instead of having a few, one or two registers, we'll have a few registers, and we'll allow on each cycle, on each state, we'll perform one operation on these registers and optionally write it back to a different register. And then we'll have some comparison that lets us take decisions based on on whether two registers are, for example, equal. And so with this data path, you can start writing control FSMs that in this case have more inputs. And so here you can see an FSM for factorial, where we have, because our data path is more flexible, we have more control inputs. Now, because of the way I've drawn this more programmable and more general data path, what you'll see, and what we'll finish seeing the next lecture, is that this actually maps directly to RISC-V instructions. So each of these states in our control FSM is just an instruction. And then the only step that we have left, right, so at a very high level, what we're going to have is something like this, where we're going to have a few more registers, and so this is going to be a register file, and we're going to have a few more operations, and this is going to be the ALU that you already built in Lab 2. And then the other bit of crucial machinery that we need is we need a memory to give us instructions, right? So the key idea and the key difference between computers and FSMs is that you have your code, right, your program is encoded in the memory itself, and you bring it from memory over time and then use it to drive the data path. So in the next lecture, we're going to see these in full detail for RISC-V. All right, that's it. Thank you.